Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were discussing Rayleigh flow in a PV diagram. We derived the expression for Rayleigh line and Hugoniot curve, and I showed you the PV diagram for those. We said that this is our starting point P1 V1 where the ratios will be 1, and then we said if I have a Rayleigh line for a given mass flow rate, it will be something like this. If the mass flow rate increases, the slope will become much higher and it will do something like this. It is, if my M1 increases, my slope is going to go from this one to a even more tilted one, more vertical one. That is what will happen. Okay. And we said if I have q equal to 0, then I am going to have a curve through this, something like this. And if my q increases, that is, if I go q positive, I am going to say it is going to go have a curve like this, or if I cool it, that is my q is negative, then my curve will go this side. This is where we stopped last time, and we found that the actual solution for the problem will be the position 2. We started at 1 and we had to go end with 2. The P2 V2 will be the intersection of these lines, Rayleigh line and the Hugoniot curve. If I cool with this particular q value, then I will end up with this particular point state 2, okay, for that particular beginning Mach number M1. Okay. If I heat it, I find that I am not going to have a solution for that particular Mach number. Okay. We will just see, we will figure out what is happening in here in detail as we go. Okay. Now, we will go to the screen where I am showing some case. I am showing so many things on this curve. Let us just look at things one by one. First, let us look at these straight lines, these 3 lines I have. I am drawing it for 3 different Mach numbers, M1 equal to 0.7, M1 equal to 1 and M1 equal to 1.5. I am drawing it for 3, and you can see that all of them passes through this point where pressure ratio and volume ratio are 1. Yeah, this is what we said, this is our starting point. From here the solution is going to go along this line that way or along the line this way, one of these two it is going to do. Now let us look at these curves that we have. These are your Hugoniot curves for different q values. I am plotting it for q equal to minus 0.5, minus 0.25, 0, that will be the center one, and then plus 0.25 and plus 0.5. Okay. So these are just some numbers, we just need to think about it as q increasing or decreasing, that is all. Okay. Now if I look at the curve, let us say I want to start at this point and I say q equal to 0 line, I am finding that the solution that can happens to be, if I think about a Rayleigh line for m equal to 1, then there is no other solution other than this. Okay. What does that mean? The flow is already at P1 and V1, it cannot go to any other P2 V2, it can just stay at P1 and V1 and nothing else. Okay, that is all it says. If I do not add heat or remove heat, there is no solution for M1, m equal to 1 flow. Mach 1 flow does not like to change, that is what this says. Okay, there is no solution for this. Okay, that is one special case. Now let us look at M1 subsonic, that is this blue straight line. Okay, if I look at that case, if I think about the bottom curves where I am cooling compared to no flow case. Okay, I am here. If I let us first pick no Q case. Q is 0, that's this red curve along with this blue line. If I think about it, there is one solution that is at P1 V1. Okay. P2 V2 can also be at P1 V1, that's a possibility, that is trivial solution, there is no change in the flow. Or I can have another solution that is sitting somewhere here, okay, which is a case that corresponds to M2 greater than 1, okay, while my M1 is less than 1, and it so happens that this particular case has entropy change negative, and that is not possible. This is corresponding to what we saw in our original BZT flows. No? We said somewhere that we have strong sudden expansion wave, as in it's like an expansion shock. Okay? It becomes an expansion shock if I think about that particular case. Okay? And in our flow where P equal to rho r T is our gas law, it is not going to be valid. For us, our delta S will be negative, that is that particular situation, and so that particular solution of the subsonic Rayleigh line cutting with this red curve for Q equal to 0 is not possible for us. Okay? That is one thing. And on the supersonic side, it does not go at all. Okay? That is on the other side, it does not go at all, there is only one possibility, it says, for Q equal to 0. Now let us pick out the same Rayleigh line, I go to cooling conditions. Simple enough to think about, the solution goes towards higher pressure and lower volume, that is it is getting more compressed. Higher pressure and lower volume means it is getting more compressed, that is I am cooling and the gas is getting more dense. Okay? That is what is happening here, and it so happens that these are corresponding to my subsonic solution, and I am cooling. This, if you go along the Rayleigh curve, I am going away from m equal to 1. That is happening along this line. If I keep on increasing my delta Q, it is going to go this way more and more. I am more and more cooling, it is going to go more and more far away from m equal to 1. Okay, and you can say that M2 is less than M1, and that is the cooling situation. That will start happening. That is one case. Now if I go the same line on heating side, that Rayleigh line is going and cutting on slight heating somewhere here, okay, where my pressure decreases and volume increases, that is the gas has expanded. I have added heat and the gas expanded. This is our standard flame, this corresponds to your flame solution. Typically they call this in combustion world the deflagration. Okay. This is your deflagration solution, and there is one more solution out here. If you go to the entropy calculations, you will find that it will be a strong deflagration as per combustion terms, and that is your delta S less than 0 condition. Okay. Again, that is not possible for our situation, unless you have an expansion shock, these kind of things will not be possible. Okay. There will be a point where I can keep on heating, and I will go to a point between this curve and the next curve, there is a particular Q value for which this is tangential to it. That is the maximum heat I can add to this system starting from a subsonic condition. Okay. That is beyond that there is no solution. If I add a heat higher than that for this magenta curve, I find that there is no solution possible. Okay. That is, the system has reached its maximum T naught star and it cannot accept any more heat, it has gone to that particular stage. Okay. Now we discussed this particular subsonic initial conditions curve for now. Next we will look at supersonic initial condition, M1 equal to 1.5, that is this cyan curve. We will look at that curve. We will again start with the Q equal to 0 Hugoniot curve along with that Rayleigh line M1 equal to 1.5. We find that this particular curve can give a solution here, P1 V1 equal to P2 V2, that is a possibility, which means it is a trivial solution, there is nothing changing in the flow, no heat added, nothing is changing in the flow, that is a solution. Or I can have another solution out there, which is again, this is the condition that corresponds to your shock, okay, normal shock. If you think about it, that point happens to be your normal shock solution, no heat added, there is just a sudden jump in solution. It is going to go M2 less than 1, I am having M1 greater than 1, and this will give you M2 less than 1 solution. That is your normal shock solution, that is possible here. Okay. That is your case there. Now we will go from here to cooling condition again. If I cool, this is going to be a green curve or the blue curve along with this cyan, wherever it meets, that meets at this point or at this point. If I think about these conditions, I am going to look at from here, it is going to this particular point or at this particular point. I am going to say that if it is at this solution marked by this arrow, you are seeing that M2 is greater than M1. I started with M1 1.5, now it is going to go above 1.5. It is going more supersonic. I am going far away from M equal to 1 because of cooling. I am going away on the supersonic curve of my Rayleigh curve this time. Okay, that is what is happening in this condition. And similarly, if I heat more, it is going to go from this Mach number to even higher Mach number. That is what is happening along this line. Now I will go to the other side where it will give me subsonic solutions. Okay. I add a little heat and I am going and sitting, it is going to give lesser Mach number solution. I do not want to say subsonic solution. It is going to give me lesser Mach number solution. I add a little heat. For M1 equal to 1.5, I am going along this line, and I added a little heat, and I find that M2 is less than M1 but still supersonic. This I am going towards M equal to 1 from M equal to 1.5, okay, along the Rayleigh line towards M equal to 1. And it so happens that I was lucky enough to get this tangential condition here for my Q values. So I just kept this number, and this is the point where it is just barely tangential. For that Q value of 0.5, for M1 equal to 1.5, I am getting almost a tangential situation. That basically says that that is the maximum heat possible, and that particular point you will get M2 equal to 1. That is, I am reaching the star condition on the Rayleigh curve. That is going to happen for this particular Q value for a M1 of 1.5. That is a special case here. Okay. Now I will go along this curve. There is another solution sitting here for a lesser heating. That corresponds to I have a shock and I have subsonic heating. Okay. That will be the other condition. I have a shock followed by subsonic heating, that will give me this particular solution. Okay. And these set of solutions, the top half of this set of two solutions on this curve and line, if you find these set of solutions are what they call the detonation solutions. Okay. This is just a shock with no heating, this is a shock with some heating, and if I add more and more heat, it is going to go to M2 equal to 1 here. That is what you will end up with finally. Okay. If I add more and more heat, it is going to go along this, the solution will keep going along this curve and finally end up here. That is what you will get in this case. Okay. Now there is one thing which I did not talk about, but I already gave you the idea basically. If I think about M1 equal to 1 condition, this particular Rayleigh line, at Q equal to 0, I told you it is already tangential and there is no other solution for heating. When I cool it, I can go either this direction and I am going to get M2 less than M1, the subsonic solutions, okay, along this direction, or I can go that side and I can get M2 greater than M1, the supersonic solutions. Okay. That is, I am starting at the star condition, M1 equal to 1 condition, right, M1 equal to 1 is this line. When I start with M1 equal to 1, I can go either direction now, I can go through a supersonic solution or a subsonic solution on my Rayleigh curve. Okay. Basically you have to keep in mind the Rayleigh curve when I am talking about this one, okay, then you can match these two things together. Okay. That is the basic idea of looking at this curve. Okay. This is called the Rankine-Hugoniot plot, okay. And we can look at this as just simple PV diagram. This gives you some set of information, and we have TS diagram which again gives you another set of information. Okay. Both are actually useful if you think about it. Okay. We looked at TS diagram where we kind of said that every solution goes towards M equal to 1, and now we can also look at a PV diagram which we just did, Rankine-Hugoniot plot, where I will say I can look at it from different points of view. There are different solutions possible, there is subsonic solution, supersonic solution, some solutions are not possible, etc. Okay. There is so much variety, and this gives you a little flavor for what is happening when flow is heated. Okay. Of course, in all this I am not telling exactly at what Mach number is the heat added to the system. Okay. I am not telling very clearly where the heat is really added. I am just going to get this solution if I add so much of heat into the duct, any point inside the duct. All I know is duct starts at point 1 and ends at point 2, and somewhere in the middle the heat was added, that is all I know. Okay. When you look at this solution on the plots we had, where we said there is a supersonic flow, there is a shock followed by subsonic heating, I said. It need not be that actually. It can be a heating followed by a shock also. Okay. I do not know where heating is really happening. Okay. It is going to give that solution if I give this much heat. That is a possibility. That is all I can say right now. Okay. And I have not really checked whether this statement is true by doing numerical examples, but I will give that as an exercise to you again. Okay. That is heating followed by shock and shock followed by heating, I believe will give you the same answer for Q's less than Q star, Q max. Okay. Currently I will just go for one numerical example. I do not have enough time in the whole course to give you more examples. I will just give you one example for a simple case, and then I will give you more complicated problems in the exercise. Okay. So I am going to say we will start with combustors. I am having some combustor. It is having a U1 of 80 meter per second, T1 of 120 degrees Celsius, P1 of 180 kilopascal. Actually, I am not going to use the pressure value, does not matter for me. Okay. And I am having some fuel injected inside and it is burnt. Now, I am going to tell that the fuel has a heating value of 45 megajoules per kilogram of fuel. If I burn 1 kilogram of fuel, it is going to produce 45 megajoules. Okay. And I am going to say this is air going in, gamma equal to 1.4 air. And I am going to assume that because of combustion, the gamma does not change, as I said in the beginning of Rayleigh flow assumptions itself. I am going to assume that in here. Okay. Even though we know carbon dioxide has a different Cp value than air, okay, we will assume that it does not change much. Okay. So we want to find how much fuel can I maximum burn in this particular flow situation. I cannot change the incoming conditions. I want to see how much can I burn inside this. Assume a constant area duct currently. Okay. Even though most combustors are not constant area duct, we will assume a constant area duct for this problem. Then only I can apply all my Rayleigh flow equations here currently. Okay. So how will I start the problem? I just have to find T naught star, right. I want to find maximum heat added, that is Q max I have to find, which is related to T naught star minus T naught 1. So I need to find T naught star. For that I need to know some parameter at the inlet. Easiest thing for us is Mach number. So I will find the Mach number here. M1 will be U1 by square root of gamma RT, ET divided by square root of 1.4 into R is 288.6 into 120 Celsius is 393 Kelvin roughly. So this is going to give me an answer of 0.2. Okay. So I picked number such that it gives nice number finally. Okay. Anyways, so I need to find T naught 1 from here, okay, because we want T naught star. So T naught 1 is equal to T1 times T naught 1 by T1 is equal to 393 into 1 plus gamma minus 1 by 2 m square, or I will just go look up my isentropic tables for that Mach number. What is T naught 1 by T1? That comes out to be 1.008 for gamma equal to 1.4, and this is going to give me an answer of 396.1 Kelvin. That is my T naught 1 value. So after this, the problem again became very simple suddenly. I am just going to find T naught star from here. Okay. T naught star from here, I will have to go and look at Rayleigh flow tables for M1 equal to 0.2 Rayleigh flow tables and find T naught by T naught star for M1 equal to 0.2. Okay. T naught by T naught star for M1 equal to 0.2 for gamma equal to 1.4 happens to be 0.174. So this is going to give me a T naught star value of 2276.4 Kelvin. Okay. So the remaining thing is just finding out how much fuel can be burnt per mass of air, okay, because we don't know the absolute mass flow rate since they did not give me area in the duct. Okay. If I know the area, I can find the mass flow rate given this information. Okay, I know density, I know U, I just need area, then I can find mass flow rate, then I can find the mass flow rate of fuel required. I didn't give you area, so we won't calculate that right now. So I just need to find Q max. T naught star minus T naught 1. So you know Cp is gamma minus 1, gamma by gamma minus 1 times R. Gamma by gamma minus 1 is 3.5 for gamma equal to 1.4 into 288.6 into those two numbers 2276.4 minus T naught 1 was 396.1. So this gives me an answer. I don't want to write the big number, I will just write 1.9 megajoules per kilogram. Okay. Once I know this, I need to find how much mass of fuel will give me this much of, okay. But there is one problem. What is this megajoules per kilogram? What is this kilogram? Weight of what? This weight of air. Okay. So now I want to find how much fuel can I add. I cannot find the fuel unless I find the air. So what I can really find is m dot fuel by m dot air. This is all I can find really if I think about it. Okay. This is going to be I want to have kilogram of fuel. I want to have that much heat produced, so I have to divide by the heating value 1.9 divided by 45. I will put the unit so that it makes things clear. Kilogram of air here, megajoules per kilogram of fuel. Okay. So now you can see that it is coming out to be kilogram fuel by kilogram air units automatically. Okay, that also one more check you need to think about. And this number comes out to be 0.042. This is the maximum fuel to air ratio that you can have in your combustor without having choking condition. That is, you are having thermal choking coming up suddenly, because I cannot heat any more. If I heat any more, what happens? I am going to have m equal to 1 forming, and suddenly the flow rate decreases everywhere and it jumps to a different curve. Oh, did I talk about that part? Maybe I missed that. So I will just go and do that one little thing, just a little detail. T versus S curve, that is a Fano curve. A curve like this is for a particular mass flow rate. If I have a different mass flow rate, if I have a lesser mass flow rate, it is supposed to be an envelope outside this. Okay, it will be something like this. Okay. So if I say that for a particular mass flow rate I have so much T naught Q star Q max, and I actually added more heat than this, then the solution will jump to another solution and sit here naturally. So I say I started here, my M1 was initially here, let us say, and I added more fuel than this Q max value, then immediately what happens is the whole flow field adjusts such that the flow at the inlet itself is decreased, it goes to the next curve, and then now it goes along this curve to reach this point. This is your final state. It reaches m equal to 1, it is going to be choked, but it starts with a lesser mass flow rate. Okay. This will start happening. Okay. This is the effect of choking. I am decreasing the mass flow rate because I added too much heat to the system. Okay. This is one extra thing. This is along the lines of what we discussed in Fano flow. So I just went through it a little fast in this particular situation. Okay. So I can give you another example where there is a shock inside, but that takes iterations and it is going to take the remaining time in class. So I said I will just put it in an exercise, and anyway I am going to put up exercise solutions also. So I decided not to do that in class. Okay. So we'll go for the next thing, which is just a small discussion where I want to link all the concepts of choking you learned till now. Okay. Typically this is not given in all the books, there are a few books which give this. So I'll go back to this particular expression. Choked mass flow rate, we had an expression which was I can write this expression, it is going to be square root of gamma by r times gamma plus 1 by 2 to the power gamma plus 1 by gamma minus 1, that whole thing. I don't need to write it here, but it is just a function of gamma and r, that is all. Okay, we will keep it like this. Of course, the mass flow rate, choked mass flow rate depends on the gas. Let us say we won't worry about the gas right now. If it is more compressible, it will be having little more mass flow rate, etc. That is there. Okay, we saw that already in each of those flows. Okay, if it is more mass flow rate, more flow can squeeze through the tube, that kind of discussion we had. Okay, that is still there, that is one aspect. Now I want to think about it in different ways. Okay, each of these terms is important. Now I am going to say, if I increase my T naught, I find that my m dot decreases. Okay, if I decrease my P naught, my m dot decreases. If I decrease my A star, my m dot decreases. Okay, of course I am keeping gas constant, if not I have to think about what is the effect of gamma inside here. We will not worry about that right now. Okay. Of course the r is in the denominator of this function, 1 by square root r is the function inside for r. If you think about that, if I increase my molecular mass, my mass flow rate increases. That is just because it is heavier molecules going through, so there is more mass going through. We won't worry about that aspect. Okay, we want to think about only compressibility, that is related to gamma in here. And we already discussed that in detail separately in each of those cases, so I won't discuss that in here. I will just look at these individual values. Okay. So if I have to go for choking, I have to decrease A star, or P naught should decrease, or T naught should increase. That is, I can have a restriction in the flow area. Okay, that is I am changing the flow geometry, or I can decrease P naught by several methods. One of the methods is by introducing friction. Okay, of course every flow has friction, we are just neglecting friction most of the times and adding it now when we want it, that is all. Okay. So can be introduced in thinking about that way, or I can think about some extra mixing happening. Okay, or some other crazy geometry that there is more drag in the flow. I put some protrusions in the inside my duct, and that is going to cause P naught loss. Okay, or maybe there is shock forming inside, that is going to have P naught loss. Lot of P naught loss mechanisms inside. They are all going to go take the flow towards choking condition eventually. Okay, I am thinking about a flow through a duct still. Okay, and in the middle I am having some P naught loss mechanisms. Or I can heat the gas, and that will take you to choking condition. In spite of all this, I can do one more thing, keeping the whole of this section constant. If I add more mass in my duct, somehow I added one more tube and I put more mass into it, I will go to a point where it will reach its maximum mass flow limit for the given area. Right? That is another way of choking it, that is mass addition based choking. Okay? It so happens that if I add mass, I also have to think about mixing, and that will decrease P naught, that will accelerate it towards choking a little earlier also. That is one more extra aspect you want to think about. Okay? But I just want to give names for each of this. Decreasing area and the flow goes towards choking is your geometric choking. This typically called friction choking, it need not be just because of friction, it can be mixing based choking also. If I have different gases, they are mixing, or I have suddenly something evaporating and so flow energy decreases, those all get into this area. I can have condensation, evaporation, those kind of things can come in this area. Or I can have here, this is your thermal choking. Okay, I can have geometric choking, friction choking, or thermal choking. By the way, in a given flow it can all be happening, okay. And when you are close to m equal to 1, all of them will be very, very critical. That is why transonic flow is very, very difficult to solve, okay. You cannot neglect any of these parameters, everything will take you to m equal to 1, okay. So that is a little more, you have to be a little more careful about it. How do I avoid choking? These are all the mechanisms that take you towards choking. So I have to do the straight opposite things. I have to think about area increasing, that is a possibility. I can think about P naught loss minimizes. You cannot increase P naught just like that, okay, in a flow unless you add extra energy to the system, okay. So I will try and minimize friction, okay. I will try and minimize P naught losses. I do not want to have normal shocks, I want to have oblique shocks instead, that kind of stuff. You want to think about, if I have protrusion in my duct, I do not want, if this is the duct, I do not want a protrusion straight in, but I may want to have a protrusion that is slant, that will have lesser P naught loss, that will help a little bit, okay. Those are all things which will take you to choking condition anyway because P naught loss, but it will be lesser P naught loss, it will postpone the choking point. Or I can think about cooling, okay, very useful thing to do. If you want to avoid choking, cooling is a very nice thing to do, okay. So by the way, if I think about a complicated situation as a supersonic combustion, okay, all of this comes into play, okay. It is a very critical situation, we will just deal with that a little bit, just this half or 20 minutes class we will think about this, okay. A supersonic combustor, and just thinking about the combustor part, I am not talking about the full scramjet, yeah, but this is the combustor inside a scramjet, let us assume, okay. I am having a duct and I am having M1 greater than 1 incoming, this is my current situation. Now I want to actually add fuel into this, typically it is a liquid fuel, so it has to evaporate, which will take some energy from the flow itself, okay. And then it is going to think about mixing, mixing will remove some P naught, and eventually I have to light it and I have to hold the flame next. When I want to think about holding the flame, typically people use either cavities or some other metal objects inside the flow. I already told you it has to be slant, right, otherwise I have more P naught losses, okay. People do not inject it always like this, I just gave a typical configuration. People may have a cavity in the wall of the duct and inject it somewhere here or wherever, depending on each configuration, different Mach numbers, it can be any of these places they will inject, and this flow that is recirculating will mix that flow with this fuel and then take it out into this region. There will be a shear layer formed here which will be oscillating, which will send out fuel and air. This is one configuration. Or I can have a configuration where there is a strut which is just a metal rod sitting inside the duct, and I send fuel through this, and some holes in here will inject fuel this way or in the side or outward, anywhere, somewhere along the direction, somewhere it will inject from inside here, and now we think about how to mix this better along with the flow. People think about this one more than this one because this one typically the fuel will stay only along the walls, which will heat the walls more, because when the combustion happens, heating happens only near the wall mainly. The walls will get hot. One of the problems with scramjets is this. Now we want to think about, if I want to use this kind of situation, now I have P naught loss more because I have an object sitting in the supersonic flow, shocks will be there. We put slant objects so that shocks are lesser, but I have to inject. If I inject along the flow, then there is a problem of they are all going together, velocity difference is less, shear is less, it is not going to mix very well. So they have to think about perpendicular injection or against the flow injection typically. When I do that, I am fighting the flow if I inject against it, so the P naught loss will be a little higher, okay. I am trying to link all the things that you have learnt in gas dynamics till now in this one application, okay. So I am resisting the flow more, so the energy of the flow will be lost more, P naught will be lost more, okay, that is going to happen. But after some time it is going to of course form a shock against this, the flow will come like this, turn around and go this flow will turn around and go, there will be a shock sitting like this in front of each of the jets. There will not be just one jet, there will be so many of them sitting in this whole region. Okay. Now as they go this way, there is flow around this also, and they are all going to mix. Now I have to think about mass addition. I just added mass and the fuel evaporated because the temperature incoming is already hot enough for me. It has evaporated, and once it evaporated, now I have to think about that is also going to occupy the space. So already if I have a constant area duct, I am having more congestion, more people are running in the same area. Okay. So there is going to be more congestion. I am getting towards choking already just by adding fuel. Now that is not enough, I have decreased P naught, I have put shocks inside, I have put a metal rod in the middle, injected fuel, mixing, everything decreases P naught, and so I am going to have lesser P naught, which is again pushing towards m equal to 1. In all this, I want to light this mixture and burn it. Okay. So I am going to think about from here, I am going to light it, and as it is traveling, I want it to burn inside here. So when it is burning, again I am adding heat to the system. If I am adding heat to the gas, I am again going towards m equal to 1. Okay. Another reason for thinking about thermal choking. Okay. Now this is thermal choking, other things where P naught decrease. So it is typically friction choking or mixing based choking or mass addition based choking. Okay. So what are the ideas people do to decrease the problems? They will typically use the area expansion. Okay. They do not ever have a constant area duct, they will have area increasing. Okay. Area increasing, or sometimes they will have semi nozzle. If you have seen some supersonic scramjet vehicles, you will see that only one side the nozzle will be, the other side there will be a free jet going like this. That is also there, part of the thing. What matters is only the pressure on the wall, so the thrust will still be there. Okay. Anyways, this is one way of handling this. There is one more problem with supersonic combustion is the flow is going extremely fast and combustion is slow. Okay. So now I have to think about the combustor should be long enough to release all the heat of the fuel before this fuel air mixture gets out of my area of interest, that is near my engine, near my scramjet if I think about. Okay. Before that it has to finish all the job, that is the idea. Okay. And of course I do not want it to be exiting at m equal to 1 because I am flying supersonic, it is a scramjet. I do not want it to be exiting at m equal to 1. I have to think about having a nozzle here and a free expansion on this side to make the Mach number slightly higher than or equal to the incoming Mach number. Okay. That is what I am thinking about. I as close to the incoming Mach number as possible. I want to think about all that. Okay. So in this whole sequence, I am starting with a supersonic flow. I added a lot of things which decreased my P naught, and I added heat finally, which took me to m equal to 1 closer by all these means. I did not talk about friction in this whole thing. Okay. Now if I think about friction also, there is friction on this rod, metal to the gas contact here, or along the wall to the gas contact, friction is there. Everywhere there is friction, and that will also take it towards m equal to 1. Okay. That is why this whole problem becomes a little more tricky. Okay. And by mistake, if you added a little extra fuel than the choking thing, the whole flow chokes, there will be a shock running straight ahead, and the whole flow becomes unstarted. The combustor is called unstarted. What happens is the flow incoming will become subsonic. It jumps and takes a subsonic solution, and they call it is no more a supersonic combustor, it is burning subsonic. So they call it unstarted condition. Okay. That will start happening if I by chance do that. And then now I have to think about how to pull the shock back in. Okay. How do you pull the shock back in? I have to increase P naught of the flow somehow. Increase the P naught of the flow or decrease my back pressure really low, so that the shock goes downstream. Think about our nozzle problem, where we keep on decreasing the back pressure, the shock goes more and more downstream. Something like that you have to think about. Then that shock will be going past this, and I can go back to starting condition. It is very difficult when I am flying using this engine and the engine is unstarting. I cannot accelerate very well and go to that condition. That is where things go wrong. Okay. This is one case. If I think about a subsonic combustion but a supersonic vehicle, a simple ramjet. Okay. Just a ramjet. I am flying supersonic, but near the combustor it is subsonic. How do I do it? Typically there will be and this is where I am going to add fuel and burn inside. Then I will have another nozzle to create thrust further. This is going to be my system. I am thinking about there is incoming supersonic flow, it is going to have choking here and it is going to go to subsonic solution. Of course, you should remember your nozzle flow conditions and you should think about if there is this is a double throat nozzle we discussed some time back. This is like, imagine there is one more duct here and there is a nozzle which made it supersonic flow, it goes through a second throat and it is going subsonic. If that is the case, it is as if shock is sitting here. This is what really happens. Shock is sitting here, m is greater than 1, it goes back to m greater than 1, jumps across to this condition, okay, and then from here I added fuel, okay, I am having subsonic condition. Of course, now I have to think about similar thing, I need some flame holder and injector, etc. There is going to be fuel added to the system and there is supposed to be a flame holder and there will be burning in here, something like that. After the burning, now it is subsonic, so it is a little easier, flow is going slow, combustion can happen within this length, okay. And after that the hot gases are supposed to be expanded. From here if I think about it, it is like a rocket nozzle problem we did in an example, right. There is a chamber where there is high pressure, high temperature gas produced and that is going out through a nozzle, expanded out, and this is how the thrust is produced in this particular situation. Okay. Now what happens if I choke this? If I choke this point and I add a little more heat, of course it has to be choked for me to get back to supersonic Mach numbers here, okay, otherwise I am taking the flow incoming supersonic and sending out subsonic is a waste and it is going to be a drag. We want it to be a thrust, okay. So you have to think about it a little bit. It is going to be accelerated back, so here it will be typically choked. If it is choked here and I add a little more fuel to this, what happens? First thing, mass choking, okay, or if I do not think about mass choking, there could be combustion, more heat release, thermal choking, okay. Oh, in all this I did not talk about friction choking, that is also there, okay. Every choking possibility is always happening there, okay. After all this, if there is choking, what happens in this region? This subsonic flow, I added some mass, it went to choking condition, mass flow going out is less than what is coming in, that means there is accumulation in this region, pressure increases, right, there is more people getting crowded here. When that happens, what happens immediately? Pressure here rises, means there will be a compression wave that is going to travel this way. There is a compression wave traveling this way that is going to strengthen the shock goes more upstream, okay. By the way, it does not go to Mach 1 here, it stays supersonic in here because I am choking there, that is typically the way they design it. Now the shock goes and sits more and more upstream. There will be a point where when the shock reaches this thinnest point, that is a critical condition. If I go anywhere more upstream, when I send more compression wave, then this shock suddenly it keeps moving like this. After this point, you know that it is unstable in this converging duct. So what happens is suddenly it jumps out of this whole thing and sits here, okay. Basically I introduced too much fuel, that compression waves came and pushed this shock ahead of this whole thing. If it is sitting here, then what happens is flow suddenly finds that there is a normal shock in front of it and so it becomes subsonic and then it goes through this. Now there is a possibility of spillage, some of the mass goes out because there is choking there and there is extra mass added there, air cannot go through in this path, so some air goes out that direction, that is how you got spillage in the system, okay. So now this can start happening and added to this, if there is some pressure oscillation inside here which is characteristic in these kind of ducts with partial closed ends. If there is a pressure pulse, it is going to be reflecting up and down inside here, and that happens, the pressure inside the system is going to be going up and down. Coupled with this, when the pressure increases, flame burns better because molecules are closer. If such a thing happens, then combustion heat release is going to be going up and down. Okay. If the heat release increases, we know it chokes better, so there is a pressure wave created. Okay. Heat release increase causes increase in pressure. Increase in pressure causes a wave to go up. Okay. That whole sequence causes a coupling, and that causes acoustic instability, thermoacoustic instability they call it. Okay. Because it is linked with the combustion also. If such a thing happens, then there is a possibility of, if I am working on the edge, then the shock can be jumping out, coming back, jumping out, coming back. Typically nobody works on that region. Okay. Typically people work safe on the inside. Okay. That is one thing you have to think about. And one more problem I just wanted to introduce because I am working on it. If I have external compression intake, again a ramjet problem, typically instead of having this kind of supersonic flow incoming on that nozzle, they can have a situation where there are oblique shocks which are decreasing the Mach number slowly, and then it goes through a situation where the area decreases and increases slightly and goes and sits with a normal shock, and then your combustor starts there. This is a replacement for this nozzle in here. Okay. That is just a replacement for this nozzle sitting in here, which is decreasing the supersonic flow to subsonic inside the combustor. If this is the situation, now there are more things that can happen in here. Okay, I will just tell you this is not in any way part of the scope of the course. I just want to go a little beyond, just we have this 5 minutes. Okay. So I am going to say, because of this sudden jump in pressure, boundary layer can now suddenly face an adverse pressure gradient, and it may separate, need not separate, it may separate. Okay. There is a possibility that it separates typically in this one. Okay. Instead of, I will just draw that region really big, instead of having a shock like this, because of this pressure gradient, the boundary layer typically must be rising like this. Instead of this, it may do something like this with a recirculation bubble sitting here. Okay. Something like this is a possibility. If such a thing happens, then now the flow has to turn a little more, so the shock comes ahead. Okay. And that changes the shape of the shock. Okay, it goes a little more ahead. When such a thing happens, they have designed it to the point that this shock goes and hits this corner. Okay. If they have done it that way and the shock slightly shifts up, what is going to happen? It is going to be more normal, there is going to be more P naught loss. There is more P naught loss, it is going to have easier choking inside. Okay. If it is easier choking inside, the compression wave will be pushed more out, and I will have the shock going out more. Okay. But when the shock goes out more, this kind of situation happens. The shock goes out of this edge, this is called the cowl. If it goes out of this edge, then I am going to have spillage, and the mass going in decreases. The mass going in decreases, and there is no extra mass added inside. What will happen? Slowly the mass inside decreases, pressure decreases. So it is like the system is experiencing a lower back pressure. If it experiences lower back pressure, slowly the shock will be pulled in. The shock is getting pulled in, suddenly the oblique shock is more and more oblique, the lesser P2 by P1. If it is lesser P2 by P1, this boundary layer tripping need not be very strong, the bubble decreases in size. Okay. And when the bubble decreases in size, there is more mass flow going in because it is the opposite effect. Now we went through a whole cycle. We started with nothing, there was a bubble formed, it grew, and then now it is decreasing. Now again it goes to a situation where if there is any disturbance, it can again form this bubble. Now what happens? This thing starts oscillating up and down like this. Okay. This is called the buzzing. Okay. This is called the intake buzz in supersonic intakes. Okay. This is also a possibility in this system. Okay. If I think about these problems, whatever I discussed in the last 10-15 minutes, they are all complicated examples which can be solved by whatever we dealt with in the whole course till now. Okay. But it is a little more complex because now I have to think about there is friction, there is also heat addition, there is also expansion, there is also mass addition. It just becomes a little more complex to deal with. It is not one at a time. We dealt with only things one at a time. We said when there is friction, there is no heat addition. When there is heat addition, there is no friction. There is no area change ever. And when there is area change, there is no friction, no heat addition. That is the way we dealt with, okay, one at a time. But in real life applications, it is all mixed up. Everything happens at the same time. Okay. That is a little more than this course scope. So we will not go into that. The next class onwards, we will think about experimental methods, experimental techniques, as in how to create a supersonic flow or a compressible flow, even subsonic, high subsonic, how to create such flows, and how to do experiments in there. Okay, probably next 5-6 classes I will be dealing with that, and then I will go into the probes, various probes that can be used. Then we will deal with some computational methods after that. See you people next class.